Module 5, Lecture A, CNNs from Scratch. By the end of this lecture, you will be able to construct a convolutional neural network using conv2D, pooling, and fully connected layers in PyTorch. Train the CNN on a small image dataset using the standard training loop and appropriate loss and metrics. And analyze model performance using accuracy, confusion matrices, and simple error inspection. Building CNN layers. Understanding conv2D kernels. A convolutional layer uses a small grid of numbers called a kernel or filter that moves across an image to transform it. At each position, it multiplies the pixel values under the kernel by the kernel's numbers and adds them up to produce a single output value. As this kernel slides over the whole image, it allows the network to detect patterns such as edges or textures. Instead of being designed by hand, the kernel values are learned during training, so the network can recognize patterns useful for tasks like identifying handwritten digits or traffic signs. In a typical convolutional layer, many small kernels slide across the input, and each one produces its own output channel. Every kernel looks at all input channels, such as the red, green, and blue of an image, but only over a small local region. As they move, they combine the local pixel information into single output values that capture useful features. Different kernels specialize in detecting different patterns, such as edges, textures, or other structures. In tasks like autonomous driving, early kernels may pick up simple features like lane markings, while deeper layers use these to recognize more complex objects, such as vehicles or pedestrians. In a convolutional layer, key design choices control how the network processes images. The kernel size sets how large an area each filter examines, so small kernels focus on fine details while larger ones capture broader patterns. The stride determines how far the filter moves each step, which changes how densely the image is sampled and how large the resulting feature map will be. Padding adds extra pixels around the image edges to preserve spatial dimensions and reduce information loss at the borders. Together, these settings shape how well the network can recognize patterns in tasks such as face verification or satellite image analysis. Python code. Understanding conv2D kernels. This script provides a simple visualization of two-dimensional convolution kernels, similar to those used in basic convolutional neural networks. It is designed to help beginners see how a kernel slides across an input and produces outputs. The implementation relies only on NumPy and keeps the resulting outputs small and easy to inspect. We begin by importing the numerical computing library NumPy in Python. This library is essential for working with arrays and carrying out mathematical operations efficiently. Using NumPy allows us to handle the data structures and calculations needed for the convolution operations that will appear later in the script. We set the random seed to 42 using the random tools from the NumPy library so that any random numbers generated are the same every time the script runs. This makes the results reproducible, meaning others can run the same code and get identical outcomes. Reproducibility is especially helpful for debugging and for sharing work, because it removes differences that would otherwise come from random number generation. We begin by creating a small grayscale image as a 5x5 grid using a numerical array. Almost all the pixel values are 0, except for a simple cross-shaped pattern in the center. The middle pixel of this cross has a value of 2, and it is surrounded by pixels with value 1. This basic pattern serves as a clear example for demonstrating how convolution operations work, and the values are stored as floating point numbers to maintain precision in later calculations. We define a 3x3 edge detection kernel in NumPy. with negative ones in the top row, zeros in the middle row, and positive ones in the bottom row. This pattern is commonly used to detect horizontal edges because it highlights differences between the upper and lower parts of the image region it processes. By using a floating point data type, the kernel can represent decimal values, allowing more precise calculations during convolution. To find the size of the output feature map after a convolution, you compute how many positions the kernel can take as it slides over the image. For the height, subtract the kernel's height from the image's height and add 1. This gives the number of vertical positions. For the width, subtract the kernel's width from the image's width and add 1. This gives the number of horizontal positions. These calculations ensure the kernel always fits inside the image as it moves across it. We check that the output dimensions of the convolution are positive to ensure the kernel can move across the entire image without going out of bounds. This validation is necessary for the convolution to be defined and to run correctly. If any output dimension is 0 or negative, it signals a configuration error, such as choosing a kernel that is too large for the image size. To store the results of a convolution, we create an output feature map as a two-dimensional array filled with zeros. Its height and width are set using the previously calculated output dimensions, so it can hold all convolution results. Initializing with zeros provides a clean starting point, where each position will later be replaced by the computed convolution value. We use a nested loop to move over every position in the output feature map. At each position, we take a 3x3 patch from the original image that matches the current location of the sliding kernel. This patch is obtained by slicing the image array from the current loop indices across 3 elements in both height and width. Extracting this patch prepares the data needed for the next step of the convolution operation. In this step of convolution, we focus on one small patch of the image and multiply each of its values with the corresponding values in the kernel. This element-wise multiplication emphasizes image features that match the kernel's pattern. We then add up all these products to obtain a single number, which represents how strongly that feature appears at this location. This value is stored in the output feature map, and repeating this process across the image produces the transformed image after convolution. The code takes the result of each convolution operation and stores it in the matching position of the output feature map. In other words, after the kernel is applied to a small patch of the image, that single computed value is written into the output. As the kernel continues sliding across the image, these stored values gradually fill in the feature map. This process builds the feature map one element at a time. We start by printing the original 5x5 pixel image to the console so we can visually inspect its local pattern. This image is stored as a NumPy array in a variable that has already been defined. Viewing this raw data lets us see exactly what will be fed into the convolution process. In other words, we examine the input image first so we understand its structure before any transformations are applied. We start by printing a short message to explain that the next output will show the kernel values. Then we display the kernel itself, which is a 3x3 matrix used for edge detection in an image. This kernel highlights changes in intensity that indicate where edges are located. Showing the kernel helps make clear the pattern it uses and how it will affect the image data during processing. We now display the resulting feature map, which is the output of our convolution operation. This feature map is a 3x3 matrix, as determined earlier from the input image and kernel sizes. By printing this matrix to the console, we can visually inspect how the convolution has transformed the image. This helps us see how the kernel has interacted with the image to emphasize certain features, such as edges. This script shows a simple example of convolution using a small grayscale image and an edge detection kernel. The image is a 5 by 5 grid with a pattern in the center, and the kernel is a 3 by 3 matrix that emphasizes horizontal edges. The code slides the kernel across the image, multiplies overlapping values, and sums them to compute the convolution at each position. This produces a 3 by 3 feature map that reveals where horizontal edges appear in the image, clearly illustrating the effect of the convolution process. Understanding pooling layers. Pooling layers in convolutional neural networks reduce the spatial size of feature maps while preserving important information. They work by sliding a small window, such as 2 by 2 or 3 by 3, over the feature map and summarizing each region into a single value. This produces a smaller feature map that still captures the key features of each area. As a result, the network becomes less sensitive to small shifts or distortions in the input image, which is important because objects in real-world images, like faces or cars, rarely appear in exactly the same position or orientation. Max pooling and average pooling are two common operations in convolutional neural networks that help simplify feature maps. Max pooling takes the highest value in each small region, emphasizing the most prominent features, which is especially useful for tasks like image classification. Average pooling instead computes the mean value in each region, giving a smoother summary that reflects overall texture or brightness. Together, these methods help the network focus on essential visual information, with max pooling highlighting distinct features and average pooling capturing a broader view of the image. Pooling layers reduce the size of feature maps, which cuts down the number of parameters and computations needed in later layers and makes models more efficient, especially on resource-limited devices like smartphones or embedded systems. By summarizing nearby activations, pooling also introduces invariance, so small shifts or rotations in the input image do not greatly change the pooled output. This helps the network recognize objects reliably, even when their position or orientation varies. Python code. Understanding pooling layers. This script gives a visual explanation of pooling layers by using TensorFlow to simulate simple pooling operations. It is designed to help you understand how pooling works by comparing different results. To use it, you should run all the cells so you can see the printed outputs and comparisons that illustrate the behavior of pooling layers. The commented line is telling you to install TensorFlow version 2.20.0. You would run this command in a terminal or notebook to make sure that specific version is installed. This step prepares your environment so TensorFlow is compatible with the rest of the script. In short, you do this before running the following code to avoid version conflicts. We begin by importing several key libraries needed for our work. The operating system library lets us interact with the system environment, and the random library allows us to generate random numbers for tasks like setting seeds or creating random data. We then import NumPy for efficient numerical computations with arrays and mathematical operations. Finally, we bring in TensorFlow, a machine learning library that we will use to build and manipulate neural network layers, including pooling layers used in this script. To make machine learning experiments reproducible, we set a fixed seed value so that random operations give the same results every time the code runs. We apply this seed to Python's built-in random system, then to NumPy's random generator, and finally to TensorFlow's random generator, all using the same value. By synchronizing the seeds across these libraries, we align all random processes and ensure consistent, predictable outcomes in our experiments. We begin by printing the TensorFlow version being used. This helps confirm that the script is running with the intended version, since different versions can change features or behavior. By displaying the version at the start, we make it easier to check compatibility and diagnose any issues that might arise later. We begin by creating a simple example feature map using a small two-dimensional array with 4 rows and 4 columns of floating point numbers. These values are chosen explicitly to form a basic grid of data that will serve as input for demonstrating pooling operations. The array is stored using the float32 data type, so it works smoothly with the TensorFlow functions used later. We first verify that the example feature map has a shape of 4 by 4 to confirm it matches the expected size. If the shape is different, the code raises a value error to indicate that the input dimensions are incorrect. This validation step is important because it prevents problems later when pooling operations are applied to the feature map. We first add batch and channel dimensions to the feature map by expanding its array dimensions, turning a two-dimensional feature map into a 4-dimensional tensor. This step is required because TensorFlow pooling layers expect inputs to include both a batch size and a number of channels. By reshaping the data in this way, we make sure the input tensor has the correct form and is compatible with the pooling operations that will be applied next. We first verify that the input tensor has the expected shape of 1 by 4 by 4 by 1, which corresponds to the required batch size, height, width, and number of channels. This check ensures the data is structured correctly before any further processing. If the shape does not match, we raise a value error that reports the expected dimensions. This validation step helps prevent downstream errors in operations that rely on a specific tensor structure. In this setup, we create a max pooling layer using the Keras tools in TensorFlow that scans the input in non-overlapping 2x2 regions. For each region, it keeps only the maximum value, and the stride of 2x2 means the window moves 2 steps at a time across the input. Using valid padding means no extra borders are added, so pooling only happens where the full window fits inside the input. This configuration reduces the spatial size of the data while preserving the most important features from each small area. We define a 2x2 average pooling layer using TensorFlow's Keras module to reduce the spatial size of the input. This layer looks at small 2x2 blocks of values and places each block with the average of its 4 values. The stride is also 2x2, so the window moves 2 steps horizontally and vertically, cutting the height and width of the input roughly in half. The padding is set to valid, meaning no extra values are added around the input, and only complete 2x2 blocks are pooled. We now apply a max pooling operation to the input tensor using the max pooling layer defined earlier. This layer moves over the input in small 2x2 regions, and for each region, keeps only the largest value. By doing this, it reduces the spatial size of the data while keeping the most prominent features from each region. The output is a new tensor where each element corresponds to the maximum value taken from its original 2x2 block. We use an average pooling layer to reduce the spatial size of the input tensor while keeping important information. This layer moves over the input in 2x2 blocks and computes the average value within each block. These averages form a new tensor with smaller height and width. Each value in the new tensor summarizes the information from its corresponding region in the original input. The code first converts the max pooled output into a NumPy array and selects the first item in the batch and its single channel, giving a two-dimensional array that is easier to handle and visualize. It then performs the same conversion for the average pooled output. This way, both max and average pooled results share the same simple array format, which makes them consistent and ready for further analysis or display. We begin by printing a short message to indicate that we are about to display the original feature map, which is a simple 4x4 grid of numbers representing our starting data. We then print this feature map so we can clearly see the values before any processing occurs. Viewing the original data first is important because it helps us understand how later transformations, such as pooling, change the feature map. We first print a short message to let the viewer know that the next output will show the result of max pooling. Then we display the max pooled feature map itself. This output is a reduced spatial version of the original feature map, created by taking the maximum value from each 2x2 block. Together, the message and the output help the viewer understand that they are looking at the compressed representation produced by the max pooling operation. We now display the result of the average pooling operation, which shows the new feature map after pooling has been applied. In this process, the spatial dimensions are reduced by replacing each 2x2 region in the original map with its average value. This transformation condenses the information while preserving the overall average characteristics of the input data. Observing this output helps illustrate how average pooling simplifies feature maps without completely losing their essential patterns. This code explains how pooling changes the spatial size of a feature map. In pooling, each 2x2 block of values in the original map is combined into a single value. This process reduces the spatial dimensions while keeping important information. Such downsampling is a key role of pooling layers in neural networks. This script shows how pooling layers work in TensorFlow by applying max pooling and average pooling to a small 4x4 feature map. After setting a fixed random seed for reproducibility and reshaping the data to include batch and channel dimensions, it creates two pooling layers with a 2x2 window and a stride of 2. The max pooling layer keeps the largest value from each 2x2 region, while the average pooling layer computes the mean of each region. The outputs demonstrate how both methods reduce the feature map from 4x4 to 2x2, summarizing the data while keeping the most important information. Flattening and linear layers. After several rounds of convolution and pooling, a convolutional network produces feature maps arranged in a spatial grid. To make predictions, this grid is converted into a one-dimensional vector in a step called flattening. Flattening takes all activations from the final feature maps and lays them out in a single long vector for each image, following a consistent order. This vector is then passed into dense layers, which combine the extracted features to make decisions, such as recognizing whether an image shows a cat, a traffic sign, or a tumor. After the features from an image are flattened into a single vector, they are passed into linear or fully connected layers. These layers learn weights for each input and add a bias to produce output values. The flattened vector captures what the convolutional network has learned, such as edges and patterns, and the linear layers learn how to combine these features. In image classification, this process turns the learned features into scores for each possible class, allowing the network to decide whether the image shows something like a zebra, a lion, or nothing of interest. When moving from convolutional blocks to linear layers, you must account for the size of the flattened feature vector, which is determined by the number of channels and the spatial dimensions of the final feature maps. This flattened size sets how many input units the first linear layer needs. You can then add one or more intermediate linear layers with nonlinear activations to learn more complex decision boundaries. For instance, in a manufacturing quality control system, convolutional layers detect surface patterns, intermediate layers separate acceptable items from defects, and the final linear layer maps these learned patterns to the specific output classes. Python code, flattening and linear layers. This lesson demonstrates how to use flattening and linear layers in a simple convolutional neural network built with TensorFlow Keras. It highlights how the output from convolutional layers is reshaped into a one-dimensional vector using a flattening step. That flattened output is then passed into dense or fully connected layers. The main goal is to understand how to connect convolutional feature maps to standard linear layers in a compact CNN model. The commented line recommends installing TensorFlow version 2.20.0 to match the code used in this project. Using this specific version helps avoid problems caused by changes in features or syntax between different releases. It is a setup step to make sure the environment is correctly configured before you run the script. We begin by importing 3 key Python libraries. The operating system library lets us work with the file system and environment settings. The random library provides tools for generating random numbers and making random choices, which is useful for tasks like setting seeds or shuffling data. Finally, we import NumPy, a numerical computing library that efficiently handles arrays and mathematical operations. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also bring in the Layers module from Keras, which provides components like convolutional and dense layers. Together, these imports prepare us to construct and train a convolutional neural network in the script. We set a fixed seed value so that any random operations in our code give the same results every time, which is important for reproducible experiments. To achieve this, we assign the seed to Python's built-in random system, then to NumPy's random generator, and finally to TensorFlow's random operations. Using the same seed across these libraries keeps all random processes synchronized and consistent, making our results easier to verify and compare. This code prints the version of TensorFlow that is currently in use. Knowing the exact version helps you check compatibility with other tools and libraries. It also makes debugging easier, since different TensorFlow versions can change features or behavior. By confirming the version, you can better understand and control how your code will run. We begin by loading the MNIST dataset using CAS, which is a standard collection of handwritten digit images used to train image processing models. The data is divided into a training set and a testing set. The training set is used to teach the model to recognize digits, and the testing set is used afterward to measure how well the model performs. Each part contains images represented as arrays of pixel values, along with labels that specify which digit appears in each image. To speed up our work, we use only a smaller subset of the data, instead of the full training and test sets. We choose 2,000 samples for training and 500 for testing. We then slice the training data and its labels so they include only these first 2,000 samples. This reduces the computational cost and makes it easier and faster to run experiments. We speed up processing and evaluation by using only a small subset of the test data. Instead of running the model on all test images and labels, we keep only the first group of samples, as specified by a chosen test size. This creates a smaller, more manageable test set, while still allowing us to check how well the model performs. We first convert the training data to floating point numbers to improve calculation precision. Then, normalize the pixel values by dividing them by 255, so they fall between 0 and 1. This normalization helps the model train more effectively and converge faster. We apply the same processing steps to the test data to keep both datasets consistent. Before using convolutional layers, we must give each image a channel dimension, because these layers expect inputs with height, width, and channels. To do this, we add a new axis to the training and test data so that each two-dimensional image becomes three-dimensional. In this new shape, the extra dimension represents the single grayscale channel. This step is essential for convolutional layers to interpret and process the images correctly. Before building the neural network model, we first print the shapes of the training and test datasets. This confirms that the data is correctly formatted and ready to be used as input. By checking the dimensions, we verify that the number of samples and the shape of each image match what the model expects. This validation step is important to avoid errors in the later stages of model construction. We define the input to our model as a 28 by 28 pixel image with one channel, which matches the grayscale images used in datasets like MNIST. This input shape is important because it determines how we set up the first layer of the convolutional neural network. We also specify that there are 10 output classes representing the digits from 0 to 9. This number of classes is used to configure the final layer so the model can output a probability for each possible digit. We build a simple sequential model in Keras for processing grayscale images of 28 by 28 pixels. The model starts with a two-dimensional convolutional layer that has 8 small filters and uses a ReLU activation function to capture basic patterns. This is followed by a max pooling layer that downsamples the feature maps by taking the maximum value in each small region, reducing spatial size. We then add a second convolutional layer with 16 filters and ReLU activation so the model can learn more complex features from the images. The flatten layer converts the multi-dimensional output of the convolutional layers into a single long vector. This step is essential because dense layers need a one-dimensional input to perform classification. By flattening the feature maps, we keep the learned spatial information while reshaping it into a form that the dense layers can process effectively. Next, we add a dense or fully connected layer with 32 units to the model. This layer uses the ReLU activation function, which keeps positive values and turns negative values into 0, adding nonlinearity to the network. By doing this, the dense layer can combine the features learned by the earlier convolutional layers and help the model capture more complex patterns in the data. We now add the final dense layer, which produces the class scores for our model. This layer uses the softmax activation function, which is well suited for multi-class classification. Softmax converts the raw outputs into a probability distribution across the 10 possible classes. In this case, those classes represent the digits from 0 to 9, allowing the model to estimate how likely each digit is for a given input. We pass a single sample from the training data through the model to make sure its input and output shapes are correctly defined. This step initializes the model's internal structures, so TensorFlow can infer the dimensions of the data moving through the network. By doing this, we verify that the model is properly set up and ready for later steps, such as training or evaluation. We explicitly build the model to define its input and output shapes. By calling the build method, we set the input shape so that the first dimension is flexible for batch size, followed by an image size of 28 by 28 with one channel. This step finalizes the model's architecture and ensures it is fully defined. Once built, the model is ready to be used for training and evaluation. The code calls the model's summary method to check the architecture, including its layers and parameters. But it redirects the output so nothing is printed to the console. This makes the summary call effectively silent while still verifying that the model is correctly built. After this check, the code prints a brief message confirming that the model has been successfully created with flatten and dense layers, emphasizing these as the main components of the architecture. Before training a model, we first compile it by choosing key settings. We select the Atom Optimizer, which is well suited for efficiently updating model weights, especially with sparse gradients. We then use sparse categorical cross-entropy as the loss function, which is appropriate for multi-class classification when the labels are given as integers. Finally, we track accuracy as the main metric, so we can monitor how many samples are correctly classified during training and evaluation. We train the model using a fit function that takes the training data and labels, and we run it for 2 epochs, so the model sees the entire dataset twice. The batch size is 64, meaning the model updates its weights after processing 64 samples at a time. Training is set to run silently, with no progress messages. We also reserve 10% of the training data for validation, so we can track how well the model performs on data it has not directly learned from during training. We evaluate the model using a separate test set to measure how well it performs on unseen data. During this step, we compute the model's loss and accuracy on the test examples and store these results. The evaluation runs silently without showing progress messages. This process tells us how well the trained model generalizes beyond the data it was trained on. We report the model's performance on the test data by printing 2 key metrics, test loss and test accuracy. Each value is converted to a standard number format, rounded to 4 decimal places, and then displayed. The test loss tells us how much error the model makes on unseen data, while the test accuracy shows the proportion of correct predictions. Together, these rounded values give a clear, concise summary of how well the model performs on the test set. To see how the flatten layer changes tensor shapes, we build a new Keras model that uses the same inputs as the original, but outputs the activations from the third layer, which is the last convolutional layer before flattening. By examining these outputs, we can observe the feature maps produced by the convolutional layers. This lets us understand how the flatten layer then converts these multidimensional feature maps into a single one-dimensional vector that can be passed to the dense layers. We take a single batch from the test dataset, usually just the first image, to inspect how the model handles an individual input. Focusing on one sample makes it easier to trace the data as it moves through the model's layers. This helps us examine intermediate outputs, such as feature maps or flattened vectors, and better understand the transformations the model applies at each stage. We use the convolutional output model to predict the feature maps for a sample batch from the test set. This means we extract the internal feature maps produced by the convolutional layers for those inputs. By turning off verbose output, we prevent extra messages from appearing during prediction. This keeps the process quiet and efficient while we focus on obtaining the feature maps. We take the flatten layer from the model, which in this case is the 5th layer, and use it to convert the multi-dimensional feature maps from the convolutional layers into a single one-dimensional vector. After applying this flatten operation to the feature maps, we convert the result into a NumPy array. This flattened vector then serves as the input to the following dense layers in the model. We first print the shape of the feature maps to see the dimensions of the data after it passes through the convolutional layers. Then, we print the shape of the flattened vector to see the dimensions after these feature maps are unrolled into a single long vector. This flattening step is essential because it converts the multi-dimensional convolutional output into a format that can be passed into the fully connected dense layers of the model. We check that the size of the flattened vector matches the number of input units expected by the dense layer. By printing the shape of this flattened vector, we can see how many units the dense layer will receive. This verification confirms that the data flowing from the convolutional feature maps into the dense layer has the correct size. Ensuring this match is essential for the model to work properly without shape or dimension errors. This script builds a simple convolutional neural network in TensorFlow Keras to show how convolutional layers connect to dense layers. It loads and normalizes a subset of the MNIST digit dataset, adds the channel dimension, and applies 2 convolutional layers. The resulting feature maps are flattened into a one-dimensional vector, which is passed to a dense layer with a ReLU activation, and then to a final dense layer with a softmax activation to classify the 10-digit classes. The model is compiled with the Atom optimizer, trained briefly, and then evaluated on a test subset to report loss and accuracy. The script also checks that the shape of the flattened vector matches the expected input size of the dense layer, highlighting how flattening bridges convolutional outputs and fully connected layers in a CNN. Training Vision CNNs. Image Normalization Basics. When training convolutional neural networks on images, normalizing the input data is essential. Raw pixel values range widely, which makes optimization harder because some parameters change too quickly while others barely move. By transforming these values into a stable, consistent range, the optimizer can take more reliable steps, and the model sees all features on a comparable scale. This leads to faster, more stable training and better performance on both the training and validation data. When working with color images, it is important to normalize each of the red, green, and blue channels separately. This means scaling their pixel values to a common range and adjusting them so each channel has a mean close to 0 and a standard deviation close to 1. Doing this keeps any single channel, such as green, from dominating simply because it tends to have higher raw values. As a result, a model, for example one recognizing traffic signs under different lighting, can focus on key features like shapes and patterns instead of being misled by brightness differences. Normalization helps machine learning models stay robust when data comes from different sources or conditions. For instance, images from studio cameras and smartphone cameras can have very different pixel distributions, and medical scans from different hospitals can vary due to equipment differences. By adjusting inputs using statistics from the training data, normalization reduces these variations and creates a more consistent input space. This allows the model to focus on meaningful patterns instead of irrelevant differences and is a standard part of the pre-processing pipeline to support stable, predictable learning. Python code. Image Normalization Basics. This material introduces basic image normalization using TensorFlow. It explains how to load images and apply simple normalization steps to prepare them for further processing. The focus is on keeping the code and concepts straightforward, clear, and concise, so learners can quickly grasp the core idea of normalizing images. The line with the exclamation mark is a shell command that installs TensorFlow version 2.20.0. You would run it in a terminal or notebook to make sure this exact version is available for the script. In the code, it is commented out, probably because TensorFlow is already installed or the environment provides it by default. Specifying the version helps ensure compatibility and prevents problems that could occur if a different TensorFlow version is used. We begin the script by importing a few essential libraries. We use the operating system library to work with things like file paths, the random library to generate random numbers and control reproducibility, and the numerical computing library NumPy for efficient array operations and random number handling. These imports provide the basic tools the rest of the script will rely on. We begin by importing TensorFlow, a powerful library used for machine learning and deep learning, so we can take advantage of its tools for handling and processing data. We then import the datasets component from Keras, which is a high-level interface within TensorFlow. This component gives us easy access to standard preloaded datasets, such as CFAR10, which we will use for our image normalization tasks. We set a fixed seed value so that any random operations in our code always produce the same results, which is important for reproducibility in machine learning. By choosing a constant seed, such as 42, and applying it to the random library, we ensure that its random numbers are consistent each time the program runs. We also set the seed for the NumPy random number generator so that NumPy operations involving randomness are repeatable. This consistent seeding makes it easier to debug models and compare results by removing variation caused by random number generation. We set the TensorFlow random seed so that any random operations it performs are reproducible. This ensures that each time you run the script, you get the same results, which is important for debugging and confirming experiments. Using the same seed value that we use for other libraries, such as NumPy and Python's random module, keeps the random behavior consistent across the entire script. This line checks and prints the version of TensorFlow that is currently in use. It helps you quickly confirm that the correct version of the library is installed. This is important because using the expected version helps avoid compatibility issues and ensures that your code runs as intended. We start by loading the CFAR10 dataset, a collection of small color images commonly used for image classification. Using the datasets tools in TensorFlow Keras, the data is automatically divided into training and testing parts. The training images and their labels are used to teach the model, while the testing images and labels are used to evaluate how well it has learned. This setup provides a standard and reliable foundation for further processing and analysis in image classification tasks. We begin by printing the shapes of the training and testing datasets to quickly see their dimensions before applying any normalization. This simple check helps confirm that the data has been loaded correctly and that the size and structure are what we expect. Understanding these dimensions early on also gives us a sense of the scale of the data we are working with. Overall, it is a good habit to verify dataset shapes at the start of any data processing workflow. To quickly demonstrate how normalization works, we first choose a small subset of the training data. We set a subset size of 8, so we only use the first 8 images. We then create a smaller data group that contains just these images. Working with this limited set makes it easier to apply normalization and clearly see its effects before using it on the full dataset. We begin by making a small copy of the training data and converting it to a 32-bit floating point format. This conversion is important because it prepares the data for normalization. Using floating point values lets us accurately scale the pixel intensities to fall between 0 and 1. This step ensures that later operations that depend on precise numeric values can be performed correctly. This step prints the minimum and maximum pixel values in the selected images so we can see the original range of pixel intensities. Knowing this range before any normalization is applied helps us understand how the data starts out. It also lets us compare how the pixel values change after normalization. Overall, it is a quick way to check the raw intensity scale of the images. We take a small subset of the image data and convert its pixel values from integers to floating point numbers between 0 and 1 by dividing each value by 255. This step rescales the pixel intensities to a standard range. Such normalization is a common pre-processing step in image processing because it makes the data more consistent and easier for machine learning models to process and learn from. We compute the mean value for each color channel across the entire subset of normalized images by averaging over the image dimensions and the batch of images. This gives us a single average value for each channel. These mean values describe the central tendency of the pixel intensities and are important for later normalization steps. We compute the standard deviation for each color channel in the small normalized image subset using a numerical method that measures variation across the first 3 dimensions of the data. This tells us how widely the pixel values are spread within each channel. Understanding this spread is important because it supports normalization steps that aim to standardize the overall data distribution. In this step, we standardize each color channel of the image data to make it more suitable for machine learning. We start with normalized images, subtract the mean value of each channel to center the data around 0, and then divide by the standard deviation of each channel. This gives each channel a mean of 0 and a standard deviation of 1. Doing this helps models train more effectively by improving convergence during learning. We check that the shape of the normalized subset is the same as the original subset to ensure the normalization process has not changed the data's dimensions. This verification is important for maintaining data integrity. By using an assertion, we can immediately detect any mismatch in shapes. Catching these issues early helps prevent errors in later processing steps. After normalizing the image data, we compute the new mean value for each color channel. To do this, we take the average across the height, width, and all images in the subset. This calculation lets us check that the normalization has shifted each channel so its mean is close to 0. Centering the data around 0 in this way is a standard image pre-processing step that can help improve model performance. Next, we compute the new standard deviation for each color channel in the normalized subset. We do this by using a standard deviation function that operates across the spatial and batch dimensions of the image array. This calculation shows how much the pixel values still vary from the mean after normalization. By checking these values, we can confirm that the data has been standardized as intended. We start by printing the original mean values of each color channel before applying any normalization. This gives us a baseline description of the image's color statistics. After normalization, we can compare the new means to this baseline to see how the transformation has changed the data. This comparison helps us better understand the effect of normalization on the image. After normalization, we print the new mean value for each channel to confirm that the data has been centered around 0. Centering the data in this way is a common step that can improve the performance of many machine learning models. By checking these means, we verify that the normalization was applied correctly and that the data is now properly standardized. After normalization, we print the new standard deviations for each color channel to check the result. This lets us confirm that the data has been adjusted, so each channel has a standard deviation of 1. Achieving this is a common goal in data preprocessing because it helps ensure that all features are on a similar scale. As a result, each feature can contribute more equally to the model's learning process. We inspect a few sample pixel values from the normalized image data to confirm that normalization was applied correctly. By printing the values of the first pixel in the first image, we can see how the original integer pixel values have been converted into floating point numbers within the desired normalized range. This quick check helps verify that the data has been properly transformed and is ready for further processing or model training. This script shows how to perform basic image normalization on the CFAR10 dataset using TensorFlow. After loading the data and selecting a small subset of images, it first rescales pixel values from their original range of 0 to 255 down to a range between 0 and 1. It then computes the mean and standard deviation for each color channel and uses these values to standardize the pixels so that each channel has a mean close to 0 and a standard deviation close to 1. The script confirms that the image shapes are unchanged and prints the original and normalized statistics, along with a sample of the transformed pixel values to illustrate the effect of normalization. Cross-entropy loss for labels. When training a convolutional network for image recognition, we often use cross-entropy loss to measure how well the model's predictions match the true labels. The network produces raw scores called logits, which are converted into probabilities and compared with the actual class. This loss is low when the model is confident and correct, and high when it is wrong or uncertain, reflecting how surprised the model is by the true label. During training, we use gradient-based optimization to minimize this loss and thereby improve the model's accuracy. In a convolutional neural network that classifies traffic signs, the model initially may assign similar scores to several classes, reflecting uncertainty. These scores are converted into probabilities, and if the correct class has a low probability, the cross-entropy loss becomes high. As training progresses, the model learns to give higher probabilities to the correct class, which lowers the loss and indicates greater confidence. This relationship between probability assignments, cross-entropy loss, and confidence is especially important in vision tasks, where how sure the model is matters as much as whether it is correct. When training with cross-entropy loss, we represent each label as an integer index, such as 0 for one class and 1 for another, instead of using one-hot vectors. The model produces raw scores for each class, and the loss function internally applies a softmax-like normalization, so we do not need to convert these scores to probabilities ourselves. For each mini-batch, we compute the loss, average it to a single value, and backpropagate this value to update the network weights. This process steadily improves the model by increasing the predicted probability of the correct label and reducing the probabilities of incorrect labels over time. Python code, cross-entropy loss for labels. This material introduces a simple example that uses TensorFlow to demonstrate how cross-entropy loss works in a tiny convolutional neural network. The main goal is to show how to correctly handle labels and logits when computing this loss. It focuses on how these values should be represented and passed into the loss function. Overall, it is a brief, practical illustration of cross-entropy loss usage in a small CNN setting. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. It forces the environment to use this exact version, so the script runs as intended and avoids compatibility problems with other versions. You typically run this command in a terminal or notebook before executing the rest of the script. In short, it prepares the correct TensorFlow library needed for the code to work properly. This code begins by importing 3 key Python libraries. It brings in the operating system library to work with files and environment settings, the random library to generate random numbers, and the numerical computing library NumPy to handle arrays and perform efficient mathematical operations. Together, these imports prepare the program to interact with the system, use randomness, and carry out fast numerical calculations. We start by importing TensorFlow, a powerful library for machine learning and deep learning. Within TensorFlow, we use Keras as a high-level interface that makes it easier to build neural networks. We then bring in the layers tools from Keras, which provide components like convolutional and dense layers. With this setup, we can conveniently define and train complex neural network models using TensorFlow's capabilities. We set a fixed seed value, such as 42, so that all random operations give the same results every time the code runs, which is important for reproducible experiments. To do this consistently, we set the seed in the standard random library, then in the NumPy random generator, and finally, in TensorFlow's random operations. Using the same seed across these libraries keeps the behavior of random processes uniform and makes results easier to compare and verify. This line displays the version of TensorFlow currently in use. It serves as a quick way to verify that the correct version is installed. By checking this, you can confirm that your environment is properly set up. This helps ensure compatibility before you run the rest of the script. The code uses Keras to load the MNIST dataset, a standard collection of handwritten digit images. It provides two sets of data, one for training and one for testing. Each set includes images and their corresponding digit labels. This separation lets us train the model on one group of examples and then evaluate its performance on different, unseen examples. To speed up training, we work with a smaller subset of the data instead of the full dataset. We set the training set to 2,000 samples and the test set to 500 samples. Then we keep only the first 2,000 images and their labels for training. This reduced dataset makes experimentation and testing faster and more efficient. We reduce the size of the test dataset by keeping only the first portion of the samples as determined by a chosen test size. This smaller subset allows faster processing during testing. We apply the same slicing to both the test images and their labels so they stay aligned and contain the same number of examples. The code converts the pixel values of the training and test images to floating point numbers and scales them to range between 0 and 1. It does this by dividing each pixel value by 255, the maximum value in an 8-bit image. This normalization step keeps the input data on a consistent scale, which helps improve the performance and stability of the neural network during training. To prepare image data for a convolutional neural network, we need to add a channel dimension to both the training and test sets. Convolutional layers expect inputs to include this channel information as part of their shape. We use a function from the numerical library to expand each image from a two-dimensional array of height and width into a three-dimensional array. In this new shape, the third dimension represents the single color channel needed for processing grayscale images in the network. This line displays the shapes of the training data and labels, so you can confirm they were processed correctly. By checking these shapes, you make sure the input dimensions match what the model expects. This step is important for debugging and for verifying that the data pipeline is working properly before you start training the model. We build a simple convolutional neural network in Keras as a sequence of layers. It starts with a two-dimensional convolutional layer that has 8 filters of size 3 by 3 with ReLU activation, taking grayscale images of 28 by 28 pixels as input. A max pooling layer with a 2 by 2 window then reduces the spatial size of the feature maps. These feature maps are flattened into a one-dimensional vector and passed to a dense layer with 32 units and ReLU activation to learn more complex patterns. Finally, a dense output layer with 10 units produces raw logits for the 10 MNIST classes. The code prints the shape of the model's output, which consists of logits, or raw prediction scores, rather than probabilities. This confirms that the final layer of the neural network is producing values suitable for a loss function that expects logits. Knowing this output shape is important to verify that the model's architecture matches the requirements of the sparse categorical cross-entropy loss being used. We define the model's loss function using the sparse categorical cross-entropy option in TensorFlow's Keras library. This loss is used for classification problems where the target labels are integers that represent different classes. We also set the option that indicates the outputs are logits, meaning raw scores instead of probabilities. This tells the loss function to correctly handle these raw scores during training. The model is now being compiled, which prepares it for training. It uses the Atom optimizer, a common and efficient choice for handling sparse gradients. The loss function is sparse categorical cross-entropy, which is appropriate for classification problems where the labels are given as integers. During training and evaluation, the model will also track accuracy so we can see how often it predicts the correct labels. The model is trained using the keras-fit method, which takes the training images and their digit labels as input. It runs for 3 epochs, meaning it goes through the entire training set 3 times. During training, it uses a batch size of 64, so it updates its weights after processing each group of 64 images. The verbose setting is 0, so the training runs without showing any progress messages on the screen. This step evaluates how well the trained model performs on the test data. Using the keras evaluation function, it calculates the model's loss and accuracy on the test images and their labels. These 2 results are saved for later use, while the evaluation itself runs silently without showing progress. This process is important because it reveals how well the model generalizes to new, unseen data. The script evaluates the trained model on the test dataset and then reports 2 key results. It first prints the test loss, computed with cross-entropy, which reflects how closely the model's predictions match the true labels. It then prints the test accuracy, which is the fraction of predictions that are correct. Together, these values provide a concise summary of the model's performance on unseen data. To manually demonstrate how loss is calculated, we begin by selecting a small batch of images from the test dataset, such as the first 4 images. We also take their corresponding labels, which represent the true values. Using this small, manageable subset, we compare the model's predictions with the true labels and compute the cross-entropy loss. This focused setup makes it easier to understand how the loss function works in practice. The code runs a batch of images through the model in evaluation mode to obtain raw logits, which are the direct outputs of the final layer. In evaluation mode, the model does not update its weights or use dropout, so the outputs are stable. These logits are unnormalized scores for each class, produced before applying an activation function such as softmax. They are needed to compute the cross-entropy loss, which compares these raw scores with the true labels. In this step, we compute the cross-entropy loss for an entire batch of data using the sparse categorical cross-entropy loss function. This function compares the true class labels with the model's predicted outputs, which are raw logits from the final layer and not yet converted into probabilities. By passing the true labels and logits into the loss function, we obtain a single loss value that summarizes how well the model performed on that batch. We then convert this loss value to a NumPy array so it is easier to handle or display later. We begin by printing the batch labels, which are the true class labels for a small set of test images, so we can see what the model is supposed to predict. We then print the batch cross-entropy loss, a single value that measures how closely the model's predicted logits match those true labels. A lower cross-entropy loss means the predictions are more accurate. Together, these outputs help us quickly assess how well the model is performing on this particular batch of data. We print a sample of the logits to verify that they are still raw model outputs and have not yet been turned into probabilities. Logits are the values produced by the model's final layer before applying an activation function, such as softmax. By viewing these logits, we can see the unnormalized scores for each class. These scores will later be converted into probabilities during the prediction step. This script shows how cross-entropy loss is used in a simple convolutional neural network built with TensorFlow. It loads a small subset of the MNIST dataset, normalizes and reshapes the images, and defines a basic network with convolution, pooling, and dense layers that output logits. The model is compiled with the atom optimizer and sparse categorical cross-entropy loss, which is suitable for integer class labels and raw logits, then trained for a few epochs and evaluated to obtain test loss and accuracy. Finally, a small batch of test images is used to manually compute cross-entropy loss and inspect sample logits and labels, highlighting the difference between logits and probabilities and illustrating how the loss function operates in practice. Accuracy metric setup. When training a vision model, accuracy is a simple way to measure how well it is performing by checking how often its predicted class matches the true label. For each mini-batch, you look at the model's output scores, pick the class with the highest score as the prediction, and compare it to the actual label for each example. You then count how many predictions are correct, divide by the batch size, and use this value as the batch accuracy. Tracking this accuracy over time shows how effectively the model is learning to classify images. To measure accuracy over a full training epoch, you apply the same process used for individual batches to the entire dataset. As you go through each batch, you count how many predictions are correct and how many images you have seen in total. At the end of the epoch, you divide the total correct predictions by the total number of images to get the epoch accuracy, which is more stable than batch accuracy. During training, this accuracy can rise dramatically as the model learns, and you should also track validation accuracy at the same time to check that the model generalizes well to new data. Accuracy is a simple and intuitive metric, but you need to understand when it works well and when it falls short. It is most reliable when classes are balanced and all mistakes have similar consequences, such as in a basic image classification task. In many real-world problems, however, data can be imbalanced, or some errors, like missing a rare disease in medical imaging, are far more serious than others. You might start by using accuracy to train convolutional networks, because it is easy to compute, but as your projects become more complex, you will need additional metrics to capture model performance more completely. Python code. Accuracy metric setup. This script demonstrates how to set up and compute an accuracy metric for a model. It uses TensorFlow while following ideas commonly used in PyTorch. The main goal is to show how to calculate accuracy for each batch during training, and then aggregate those results to obtain accuracy for the entire epoch. This command installs TensorFlow version 2.20.0. Specifying the version helps ensure the code behaves as expected and remains compatible with the rest of the project. Different TensorFlow versions can change how functions work or how fast they run, so fixing the version standardizes the environment. This makes the script more reliable and easier to reproduce on different systems. We start by importing 3 key libraries for our script. The operating system library lets us interact with the system, for example, to work with files or environment settings. The random library provides tools to generate random numbers, which we can use for tasks like shuffling data or controlling randomness. Finally, the numerical computing library NumPy gives us efficient support for arrays and mathematical operations that we will rely on throughout the code. We start by importing TensorFlow, a main library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We then import the layer components from Keras so we can assemble different kinds of neural network layers, such as convolutional and dense layers, to form the overall model architecture. To make our results reproducible, we set fixed seed values for all the random number generators we use. We first set a seed for Python's built-in random module, so its random operations give the same outcome each time. Then, we set a seed for the NumPy random number generator, so NumPy's random values are also consistent across runs. Finally, we set a seed for TensorFlow's random number generator, which ensures that weight initialization and other random processes in our machine learning experiments behave the same way every time we run the code. This line displays the version of TensorFlow currently in use. Knowing the exact version is important because different versions can change how features work. It helps you check compatibility with other tools and libraries. It is also useful for debugging, since version differences can cause unexpected behavior. We begin by loading the MNIST dataset using Keras, which is a standard collection of handwritten digit images used to train image processing models. The data is divided into a training set and a testing set. The training images and their labels are used to teach the model to recognize digits, while the testing images and labels are used afterward to measure how well the trained model performs. This split provides a common and reliable way to prepare data for machine learning experiments. To speed up processing during development, we work with a smaller subset of the data. We limit the training set to 2,000 samples and the test set to 500 samples. We then slice the training data so that only the first 2,000 images and their matching labels are used. This reduced dataset makes it faster to train and evaluate the model while we are still building and testing it. We take the full test dataset and its labels and cut it down to a smaller subset by keeping only the first group of samples up to the number specified for testing. This reduced set is then used for evaluation. Working with a smaller portion of the data makes the testing process faster and easier to manage, while still allowing us to assess model performance efficiently. We normalize the pixel values in both the training and test datasets by first converting them to a floating point format, and then dividing each value by 255. This changes the pixel range from 0 to 255 down to a range between 0 and 1. Putting all inputs on this consistent scale is important because it helps the neural network train more efficiently and improves its overall performance. To prepare image data for convolutional layers, we need to add a channel dimension to both the training and test sets. This means expanding each image array so it has an extra dimension at the end that represents the single color channel. Using a function that expands the array dimensions, each image becomes a 28 by 28 by 1 array. The last dimension indicates the grayscale channel, which allows the convolutional neural network to process the images correctly. We check that the training and test images have the expected shape so they are ready for our convolutional neural network. Each image should be 28 by 28 pixels with a single channel, which is standard for grayscale data. Confirming this shape for both the training and test sets ensures the data is correctly formatted for the model. This step helps prevent errors when we feed the images into the network. We build a Keras sequential model by stacking layers in order. First, we use a two-dimensional convolutional layer with 16 3x3 filters and ReLU activation, taking 28 by 28 grayscale images as input. We then apply a 2x2 max pooling layer to reduce the spatial size, followed by another convolutional layer with 32 3x3 filters and ReLU, and another max pooling layer. After these convolution and pooling stages, we flatten the feature maps into a one-dimensional vector and pass it to a dense layer with 64 units and ReLU to learn higher-level patterns. Finally, we use a dense output layer with 10 units and a softmax activation to produce class probabilities for the 10 categories in our classification task. The model is being prepared for training by choosing specific settings. It uses the Atom optimizer with a learning rate of 0.001, a common and efficient choice for training neural networks. The loss function is set to sparse categorical cross-entropy, which is appropriate when class labels are integers for different classes. No additional metrics are specified, so only the loss will be tracked during training. We begin by choosing a batch size of 64, which sets how many samples are processed together. From the training images and labels, we create a TensorFlow dataset and shuffle it so the samples are in random order, helping the model avoid learning patterns based on sequence. The shuffle step uses the full training set size as its buffer and a fixed seed, so results are reproducible. Finally, we group the data into batches of the chosen size so the model can train on manageable chunks at a time. To evaluate the model, we first prepare the test dataset by creating a TensorFlow dataset from the test images and labels, using a method that slices the data into manageable parts. We then group these slices into batches, using a predefined batch size. This batching step is important because it lets the model process many samples at once, making evaluation more efficient and scalable. To compute accuracy for a batch of predictions, we first use a function that finds the index of the largest value in each prediction, which gives the most likely class for each input. We then compare these predicted class indices with the true class labels to see which ones match. This comparison produces a set of true or false values, which we convert to ones and zeros. Finally, we take the average of these numbers to obtain the batch accuracy, representing the proportion of correct predictions. We train the model for 2 epochs, meaning it passes through the entire training dataset twice. For each epoch, we track how many predictions are correct and how many samples we process. As we loop over the dataset, we take batches of images and labels, run them through the model to get raw prediction scores, and compare these scores to the true labels to compute the loss. Using TensorFlow's gradient tape, we then calculate how the loss changes with respect to the model's trainable variables, and use these gradients to update the model's weights so it can learn from the data. To evaluate a batch, we first compute its accuracy by comparing the predicted classes from the logits with the true labels and taking the average. We then find the batch size by reading how many samples are in the current set of images. Finally, we multiply the batch accuracy by this batch size using a precise floating point value to obtain the total number of correct predictions in the batch. The code keeps track of running totals for each training epoch by updating 2 main counts. It adds the number of correctly predicted samples in the current batch to the total correct predictions so far in the epoch. At the same time, it adds the batch size to the total number of samples processed in that epoch. These running totals are then used to compute the overall accuracy for the entire epoch. To compute epoch accuracy, we divide the total number of correct predictions by the total number of samples processed in that epoch. This value represents the overall proportion of correct predictions for the entire epoch. We then report the epoch number together with this training accuracy, usually rounding it to 4 decimal places for clarity when viewing the results. To evaluate the model, we keep track of 2 running totals: how many predictions are correct and how many samples we have processed. We loop over the test dataset in batches, and for each batch, we run the model in inference mode so its weights do not change. We compute the batch accuracy by comparing the model's predictions with the true labels. Then multiply this accuracy by the batch size to get the number of correct predictions in that batch. We add this to the total correct count and add the batch size to the total sample count, repeating this process until all test batches have been processed. The code keeps track of running totals needed to compute test accuracy. For each batch, it adds the number of correctly predicted samples to the overall count of correct predictions. It also adds the batch size to the total number of samples processed. After all batches are evaluated, these totals are used to calculate the overall test accuracy. To find the final test accuracy, we divide the total number of correct predictions by the total number of predictions made. This ratio gives the overall accuracy of the model on the test dataset. We then display this test accuracy, rounding it to 4 decimal places to make the result easier to read and interpret. This script builds a small convolutional neural network in TensorFlow to classify images from the MNIST dataset. It loads and normalizes a subset of the data, then defines convolutional and dense layers and compiles the model with the atom optimizer and sparse categorical cross-entropy loss without specifying metrics. Training is done manually over 2 epochs by looping through batches, computing predictions, comparing them to the true labels to estimate accuracy, and updating the weights with gradient descent. After training, the script evaluates the model on a separate test set in a similar way and prints the training accuracy for each epoch along with the final test accuracy to show how well the model performs on unseen images. Evaluating CNN performance. Confusion matrix basics. A confusion matrix is a key tool for understanding how a convolutional neural network behaves beyond simple accuracy. It is a grid where each row represents the true class label and each column represents the model's predicted label. The diagonal cells show correct predictions, while the off-diagonal cells show specific types of errors. By examining this grid, you can see not just how often the model is wrong, but exactly which classes it confuses, giving deeper insight into its performance. An overall accuracy score for a convolutional neural network does not tell you what kinds of mistakes it makes. A confusion matrix breaks this down by showing how often each true class is predicted as each possible class. For example, in medical image classification, it might reveal that healthy tissue and benign lesions are usually identified correctly, but malignant tumors are often misclassified as benign, which is a very serious error. In areas like traffic sign recognition, the confusion matrix similarly exposes systematic misclassifications and helps guide better data collection and model design. A confusion matrix is essential for understanding how a classifier performs on each class, especially when the data are imbalanced. In a defect detection task, where most items are fine and only a few are faulty, overall accuracy can look high even if the model misses many rare but critical defects. By examining the rows and columns of the confusion matrix, you can see which classes are correctly identified, which are confused with others, and how severe these errors are. This information guides decisions about collecting more data, redefining classes, or adjusting the loss function, so the model becomes truly effective for its intended use. Python code. Confusion matrix basics. This script introduces the basics of confusion matrices using a small convolutional neural network trained on MNIST digit images. The emphasis is on how to evaluate the model's performance rather than on the details of training. By examining the confusion matrix, you can see where the model predicts correctly and where it makes mistakes across different digit classes. The line starting with an exclamation mark is a shell command that installs TensorFlow version 2.20.0 rather than Python code. It is used to make sure that this exact version of TensorFlow is available before running the script. Specifying the version is important because different TensorFlow versions can change features and behavior. By fixing the version, you help keep the environment consistent and avoid compatibility problems. We begin by importing a few key Python libraries. The operating system library is included for potential interaction with the system environment, even though it is not directly used here. We also import the random library to generate random numbers and control reproducibility. Finally, we bring in NumPy, a numerical computing library that we will rely on heavily for working with arrays and performing mathematical operations throughout the script. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layers module from Keras so we can assemble key components of the network, such as convolutional and dense layers. Together, These imports provide the essential tools needed to build and train a convolutional neural network on the MNIST dataset. We set a fixed seed value of 42 to make our results reproducible. This seed initializes the random number generators in Python's built-in random module, in NumPy, and in TensorFlow. Using the same seed ensures that all random operations in these libraries produce the same outputs every time the code runs. This consistency is essential for reliable debugging and for accurately comparing results across different runs. This line displays the version of TensorFlow currently being used in the script. It provides a quick check that the environment is running the expected TensorFlow version. Confirming the version helps ensure that the code is compatible with the library and that results can be reproduced reliably. We begin by loading the MNIST dataset using Keras, which is a standard collection of handwritten digit images used to train image processing models. The data is divided into training and test sets, and each image has a label indicating which digit it represents. The training set is used to teach the model to recognize digits, while the test set is used afterward to measure how well the model has learned. This loading step is essential because it provides the data needed both to train the model and to evaluate its performance. To speed up processing and experimentation, we work with a smaller subset of the data. We set the training set size to 4,000 samples and the test set size to 1,000 samples. Then we simply take the first 4,000 entries from the original training data and their labels. This reduces the overall dataset size, allowing models to train and evaluate more quickly. To speed up evaluation, we use only a smaller subset of the test data instead of the full set. Specifically, we select the first 1,000 test images along with their labels. This reduced sample makes the evaluation process faster, while still giving a meaningful indication of how well the model performs. The pixel values in the training images are first converted to floating point numbers so they work correctly with later computations. Each value is then divided by 255 to scale all pixels into a range from 0 to 1. This normalization is a standard pre-processing step that helps the neural network train more effectively and remain stable. The same conversion and scaling are applied to the test images to keep the training and testing data consistent. To prepare image data for a convolutional neural network, we need to add a channel dimension to both the training and test sets. Convolutional layers expect inputs to include this channel dimension as part of their shape. We use a function from the numerical library to expand each image array, turning it from a two-dimensional array into a three-dimensional one. In this new shape, the last dimension represents the single channel of grayscale images. This step is essential to put the data into the correct format for the model to process. Before building the model, we first check that the number of training samples matches the number of training labels by comparing the size of their first dimensions. We do the same for the test data, making sure the number of test samples equals the number of test labels. These simple checks help catch mismatches early and prevent errors during model training and evaluation. We build a simple convolutional neural network in Keras as a sequence of layers. It starts with a two-dimensional convolutional layer with 8 filters of size 3 by 3 using ReLU, taking 28 by 28 grayscale images as input. A 2 by 2 max pooling layer then reduces the spatial size of the feature maps, and the result is flattened into a one-dimensional vector. This is passed to a dense layer with 32 ReLU units, followed by a final dense layer with 10 units and a softmax activation. The last layer outputs class probabilities for the 10-digit categories in the MNIST dataset, allowing the model to learn and classify handwritten digits. To prepare the model for training, we compile it by setting the key training options. We choose the Atom optimizer, which is well suited for efficient learning, and we use sparse categorical cross-entropy as the loss function, which matches multi-class classification tasks with integer labels. We also track accuracy as a metric so we can monitor how well the model performs during training and testing. With this configuration, the model is ready to learn effectively from the data. We train the model using the keras fit method, which takes the training data and labels as input. The model runs for 2 full passes over the dataset, called epochs, and uses a batch size of 64 samples before updating its weights. Training is set to run silently without printing progress. In addition, 10% of the training data is held out as validation data to monitor performance during training. The code checks how well the trained model performs on the test data by calling the model's evaluation function with the test images and their true labels. Detailed output is turned off, so the evaluation runs quietly. This process returns 2 key metrics: test loss, which reflects the model's error on the test set, and test accuracy, which is the fraction of images classified correctly. Together, these values show how well the model generalizes to new, unseen data. We report the model's performance by printing its test accuracy on a subset of the data. The accuracy is a decimal value, so we round it to 4 decimal places to make it easier to read and interpret. This rounded value is then included in a short message that clearly summarizes how well the model performed on the test set. The trained model is now used to predict class probabilities for the test images. Each test image is passed through the model, which produces a probability distribution over the 10 possible digit classes. In other words, for every image, the model estimates how likely it is to be each digit from 0 to 9. The verbose setting is turned off, so these predictions are generated quietly and efficiently. In this step, we turn predicted class probabilities into final class labels. We do this by using a function that finds the position of the highest probability for each test sample. That position, or index, represents the most likely class. As a result, we convert each probability distribution into a single predicted class for every sample. We first check that the number of predicted labels matches the number of true labels by confirming that both arrays have the same length. This validation step ensures that each prediction corresponds to a real test example. It is essential because any mismatch could cause errors in later analysis. In particular, it helps prevent problems when computing evaluation metrics, such as the confusion matrix. To manually compute a confusion matrix for the MNIST dataset, we start by noting there are 10 classes, 1 for each digit from 0 to 9. We then create a 10 by 10 matrix filled with zeros to hold the counts. Each row of this matrix represents a true digit label, and each column represents a predicted label. As we compare true labels to model predictions, we update the corresponding cell in the matrix. This lets us see how often each digit is correctly classified and where the model makes mistakes. To build a confusion matrix, we go through each pair of true and predicted labels in the test set and update the matrix accordingly. For every pair, we find the cell at the row of the true label and the column of the predicted label and increase its count by 1. Repeating this for all test examples records how often each actual class is predicted as each possible class. The final confusion matrix then summarizes the model's performance across all classes. We first check the shape of the confusion matrix to confirm its dimensions match the number of classes in our problem. Then we compute its trace, which is the sum of the values along the main diagonal. Each diagonal value counts cases where the predicted label matches the true label. Adding them up gives the total number of correct predictions, providing a quick summary of how many instances the model classified correctly. The code prints a message that it will display the top left 3x3 block of the confusion matrix, focusing on the first 3 classes. It then outputs this small section of the matrix, showing the counts of true labels versus predicted labels for these classes. This allows you to quickly assess how well the model is performing on the initial classes without examining the entire confusion matrix. To find misclassified examples, we compare the predicted labels with the true labels and identify the positions where they differ. A numerical tool is used to locate these mismatches and return their indices. We then check how many indices were found, which tells us the total number of incorrect predictions. This count provides a quick overview of model errors and helps guide further analysis or debugging. We examine the first few misclassified examples by looping over their indices, and for each one, printing the index, the true label from the test set, and the label predicted by the model. This quick check lets us directly compare what the model thought with the actual answer. By inspecting these specific mistakes, we can better understand where the model is going wrong and identify possible ways to improve its performance. This script shows how to use a confusion matrix to evaluate a simple convolutional neural network on a small subset of the MNIST digit dataset. It prepares the data by normalizing and reshaping the images, builds a basic convolutional model, and trains it briefly with a validation split. After training, the model is evaluated on test data and its accuracy is printed. The script then generates predictions, manually constructs the confusion matrix comparing true and predicted labels, and reports its shape, the number of correct predictions, and a small portion of the matrix. Finally, it identifies and prints the first few misclassified examples to highlight where the model makes errors and how its performance might be improved. Reviewing misclassified images. After checking your model's accuracy and confusion matrix, the next step is to look directly at the misclassified images. Comparing each image with its true label and the model's prediction turns abstract metrics into concrete visual insights. This helps you judge whether each error is understandable, such as confusing similar-looking digits or truly surprising. By doing this qualitative analysis, you can distinguish mistakes caused by ambiguous or messy data from those that reveal deeper problems with the model itself. When reviewing misclassified images, look for recurring visual patterns that connect different errors rather than treating each mistake in isolation. For instance, if small dogs are often labeled as cats when seen from behind or in poor lighting, the model may be relying too heavily on silhouette or ear shape. In medical imaging, if subtle lesions near the image borders are frequently missed, this may point to noise, biased training data, or pre-processing problems. Identifying these systematic patterns helps you target specific improvements and ultimately enhance overall model performance. Reviewing misclassified images helps you refine both your model and your dataset by revealing patterns in its mistakes. If many errors involve blurred or underexposed images, you can add more training data with those conditions. And if the model confuses similar classes, such as different bird species, you can collect more detailed or higher resolution examples. In safety-critical applications like autonomous driving, detecting misclassifications such as stop signs labeled as speed limits guides focused data collection and model adjustments. This kind of systematic review creates a feedback loop that improves model design, data quality, and ultimately the reliability of computer vision systems. Python code, reviewing misclassified images. This script trains a small convolutional neural network using TensorFlow on the MNIST dataset. then visually reviews where the model makes mistakes. After training, it identifies images the network classified incorrectly and displays a selection of these misclassified digits. This helps you see specific examples of errors and better understand the model's weaknesses. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. It is usually run in a Jupyter notebook or similar environment. The purpose is to make sure that this exact TensorFlow version is available before the rest of the script runs. This helps keep the code compatible and consistent with the TensorFlow features it depends on. We begin by importing a few standard libraries needed for the script. The operating system library is included to allow interaction with the system environment, even though it is not directly used in this short example. We also import a random number library, which will later help us set deterministic seeds. Finally, we bring in a numerical computing library, which we will rely on heavily for working with arrays and performing mathematical operations throughout the script. We begin by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We then import the layers tools from Keras, which provide the basic components for constructing the different parts of a neural network. With these imports in place, we have the essential tools needed to define and train a convolutional neural network for image classification. We begin by setting a seed value, such as 42, so that any random operations give the same results every time we run the code. To do this consistently, we set the seed in the standard random library, in NumPy, and in TensorFlow. Using the same seed across these libraries makes our experiments deterministic and ensures they are reproducible. This line checks and prints the version of TensorFlow that is currently in use. It helps you quickly confirm that the correct version of the library is installed. This is important because using the intended version ensures compatibility and helps your code run as expected. We begin by loading the MNIST dataset using the dataset tools provided in Keras. This call returns training images with their labels and test images with their labels in two separate groups. The data consists of images of handwritten digits, which are widely used to train and evaluate image classification models. Using this built-in function gives us quick access to a standard, pre-processed dataset that is ready for model training and testing. To speed up training, we limit the dataset size by using 800 samples for training and 200 for testing. We take only the first 800 entries from the training data and select the matching labels for these samples. This reduced dataset allows the model to train more quickly while still providing enough examples to learn useful patterns. We limit the test data to the first 200 samples to make evaluation faster and easier to handle. This smaller subset still allows us to assess performance without processing the entire test set. We apply the same selection to both the images and their labels, so they stay correctly matched. This keeps the reduced test set consistent and reliable for further analysis. We first check that the number of training samples matches what we expect by confirming that the size of the training data along its first dimension equals the specified training sample count. We do the same for the test data, making sure its first dimension matches the expected number of test samples. These simple checks verify that our data slicing was done correctly and help catch unexpected changes in data size early, preventing errors in later processing steps. The training data is first converted to a floating point format to allow precise calculations. Then each pixel value is divided by 255 so that all values fall between 0 and 1. This process, called normalization, puts the input data on a consistent scale. Having inputs in this range helps the neural network train more effectively and improves how quickly it converges during learning. We expand the dimensions of the training and test datasets by adding a new axis at the end to create a channel dimension. Convolutional neural networks require input data to include this channel information and to follow a specific shape. By adding this extra dimension, we make sure the data matches the expected input format of the CNN model and can be processed correctly. To set up a convolutional neural network, we first determine the input shape by looking at the dimensions of the training images, ignoring the batch size. These dimensions define the structure of the model's input layer. We then print this input shape to verify it is correct, which helps ensure the data is properly formatted for the network. We build a simple, sequential Keras model for image classification by stacking convolutional and pooling layers, then fully connected layers. The model starts with a two-dimensional convolutional layer with 8 filters of size 3 by 3 and ReLU activation, followed by a 2 by 2 max pooling layer to reduce spatial size. A second convolutional layer with 16 3 by 3 filters and ReLU activation is added, followed by another 2 by 2 max pooling layer. The output is then flattened into a one-dimensional vector and passed to a dense layer with 32 units and ReLU activation to learn higher-level patterns. Finally, a dense output layer with 10 units and softmax activation produces class probabilities for the 10-digit classes from 0 to 9. Before training a model, we first compile it by choosing key components. We select the atom optimizer, which is well-suited for efficiently handling sparse gradients. We then set the loss function to sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are integers. Finally, we track accuracy as a metric so we can see how often the model's predictions match the true labels during training and testing. The code uses TensorFlow's configuration tools to check which graphics processing units are available. It looks up all physical devices of type GPU to see how many can be used for computation. It then prints the number of detected GPUs, which helps you understand the hardware resources you have for running the model. We train the model using the Keras fit method, which takes the training data and labels and adjusts the model's parameters. We set it to run for 3 epochs, so it goes through the entire training set 3 times. The batch size is 64, meaning it updates the model after processing 64 samples at a time. Training output is silenced by setting the verbosity to 0. We also reserve 10% of the training data for validation, so the model's performance can be monitored during training. This code checks how well the trained model performs on the test data. It calls the model's evaluation function to compute the loss and accuracy, which indicate how well the model predicts unseen examples. Detailed output is turned off during this step to keep things simple. Finally, it prints the test accuracy rounded to 3 decimal places, giving a clear summary of the model's performance on new data. The code uses the trained model to predict class probabilities for the test dataset by feeding in the test images and producing a probability distribution over all possible classes for each image. This means the model estimates how likely each class is for every test image. The verbose setting is turned off so that no detailed logs are printed during prediction, keeping the output focused only on the final probability results. The code takes the predicted probabilities for each class and turns them into final class labels by finding which class has the highest probability for each test sample. It uses a function from the numerical library that returns the position of the largest value along the class dimension. This position corresponds to the most likely class for each image in the test set. We use a function from the numerical library to find the positions where the predicted classes do not match the true classes. These positions mark the test examples where the model makes mistakes. By identifying these incorrect predictions, we can focus our analysis or visualization on the specific cases where the model is failing. We first check whether there are any misclassified images by looking at the size of the array that stores their indices. If its size is 0, it means the test subset has no misclassifications. In that case, we inform the user that no misclassified images were found. To prevent later code from failing when it expects at least one index, we then replace this empty array with one that contains a single placeholder value. We begin by setting a limit of 9 misclassified images to keep the number of examples manageable for visual review. From the full list of misclassified image indices, we then select only the first 9. This slicing step ensures we work with a small, focused subset of misclassified examples. Limiting the number in this way makes it easier to visualize and analyze the model's errors later. The code reports a brief summary of misclassified images. It first prints the total number of incorrect predictions by converting the size of the misclassified index list into an integer. Then it prints how many of these examples will actually be displayed, based on the size of a selected index list. This second number shows how many misclassified images will be visualized, up to a maximum of 9. We use the pyplot module from the matplotlib library to create visualizations in Python. This tool lets us plot and display images from our dataset. By showing the images that the model classified incorrectly, we can visually inspect them and better understand where the model's predictions went wrong. To visualize misclassified images in a grid, we first fix the number of columns to 3 and then compute how many rows are needed by dividing the number of selected misclassified examples by 3 and rounding up. This calculation, done with a ceiling operation, ensures there are enough rows to display all images. We then use a plotting library to create a figure with subplots arranged in this grid of rows and columns. The figure size is set to 6 by 6 inches to keep the display compact and easy to view. The code makes sure the axes object is always a simple one-dimensional sequence by converting it to a NumPy array and flattening it. This is important when plotting multiple images in a grid, because it provides a consistent way to handle the axes. With the axes flattened, the code can loop through each subplot in order, without worrying about how the grid was originally structured. This leads to cleaner and more reliable plotting logic. We loop through each display axis together with a selected misclassified example, and for each pair, we pull out the corresponding image from the test set and reshape it into a simple two-dimensional array. We then look up the correct label from the test labels and the model's predicted label from the prediction results. This process prepares each misclassified image, along with its true and predicted labels, so we can visually compare them in the next step. The code uses a plotting library to display the image data stored in the image variable on a subplot. It renders the image in grayscale by setting the color map to gray. This simple visualization makes it easier to inspect and analyze images that were classified incorrectly. This code assigns a title to each subplot in the grid of misclassified images. It uses a formatted string to show both the true label and the predicted label for each image. By displaying these two labels together, it becomes easy to visually compare what the model predicted with the actual label. This helps you quickly see and understand where the model made mistakes. This command removes the axis ticks from the current subplot. By hiding these numerical markers around the edges, the plot looks cleaner and less cluttered. This helps direct the viewer's attention entirely to the image itself, without distraction from labels or tick marks. The code goes through any subplot areas that are not being used and turns off their axes. By hiding the ticks and labels on these unused plots, it prevents empty or distracting elements from appearing. This keeps the overall visualization clean and directs attention only to the images that are actually shown. The code first uses a layout adjustment function from matplotlib to make sure all subplots fit neatly in the figure without overlapping, which is especially helpful when there are many subplots. This function automatically adjusts the spacing so everything is clearly visible. After the layout is set, the code calls the display function from matplotlib to render the figure on the screen. This allows you to visually examine the misclassified images and compare their predicted labels with their true labels. This script trains a simple convolutional neural network in TensorFlow to classify handwritten digit images from the MNIST dataset, using only a small subset of the data for faster training. After training, it evaluates the model's accuracy on a separate test subset, and then looks for images the model classified incorrectly by comparing predicted labels with the true labels. If misclassified examples exist, it selects up to 9 of them and displays their images in a grid using a plotting library, showing both the correct and predicted labels. If there are no misclassifications, it reports this and instead displays the first image from the dataset. To make the results reproducible, the script sets deterministic random seeds before running the training and evaluation steps. Spotting overfitting patterns. When evaluating a convolutional neural network, you should look beyond accuracy and check whether it is overfitting to the training data. Overfitting occurs when the model memorizes noise or labeling errors in the training set instead of learning general features, which leads to strong performance on training images but weak results on validation or test images. For example, a network might recognize fruits well in the training set, but fail on new images taken under different conditions. By tracking and comparing performance metrics over time for both training and validation sets, you can see whether the model is truly learning patterns that generalize or simply memorizing the training examples. During training, pay close attention to how the training and validation curves differ. If training accuracy keeps improving, but validation accuracy stops improving or gets worse, or if training loss keeps decreasing while validation loss does not, the model is likely overfitting to the training data. This means it may be learning quirks or artifacts specific to the training set instead of general patterns, such as scanner artifacts in medical images. Detecting these signs early allows you to shorten training, adjust the model architecture, or add regularization to reduce overfitting. To detect overfitting beyond simple metrics, examine how your model behaves on different subsets of data and under small distribution changes. For instance, if a convolutional neural network does well on images that closely match the training set, but fails on images with different lighting or backgrounds, it is not generalizing well. A model that works on clean studio photos of dog breeds, but fails in more varied real-world scenes, is likely overfitting to the training data. By comparing performance across such scenarios and studying patterns in the confusion matrix, you can identify specific weaknesses and distinguish a truly robust model from one that is mainly memorizing the training set. Python code, spotting overfitting patterns. This script demonstrates how convolutional neural networks can overfit in a simple way. It uses TensorFlow to train very small image models and then compares how well they perform on the training data versus separate validation data. By observing the difference between these performances, you can see clear patterns of overfitting. This command installs TensorFlow version 2.20.0. Using this exact version makes sure the script runs as intended and prevents problems that might occur with different TensorFlow versions. In short, it locks in the specific version the code was designed to use helping avoid compatibility issues. We start by importing 3 key tools. The operating system module lets us interact with the system, for example, to work with files or environment settings. The random module provides random numbers and operations, which are useful for tasks like shuffling data. Finally, the numerical computing library gives us efficient ways to handle arrays and perform mathematical operations on large datasets. We begin by importing TensorFlow, a main library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layer components from Keras so we can define parts of the network, such as convolutional and dense layers. This setup provides the basic tools needed to construct and train the convolutional neural networks used in the rest of the script. We set a fixed seed value to make our experiments reproducible. This means we first set the seed for Python's built-in random number generator, then for NumPy's random functions, and finally for TensorFlow's random operations. Doing this ensures that any randomness, such as weight initialization in TensorFlow, behaves the same way every time we run the code. As a result, we can compare results reliably and debug models more effectively. This code simply prints the version of TensorFlow that is currently in use. Knowing the exact version helps you check compatibility with your code and libraries. It is especially important when you rely on specific features that may change between versions. It also helps when debugging issues that might be caused by differences in the TensorFlow environment. We begin by loading the CFAR10 dataset using Keras, which is a standard collection of small images used to train machine learning models. The data is divided into a training set containing images and their labels, and a separate test set. We train the model on the training set and then evaluate it on the test set. This separation is essential because it lets us measure how well the model performs on new unseen data and how well it generalizes beyond the examples it was trained on. The code first checks that the training images have the correct shape, meaning each image is 32 by 32 pixels with 3 color channels. This confirms the image data is properly formatted for use in a convolutional neural network. It also verifies that each training label is a single value, ensuring the labels are structured correctly for a classification task. Together, these checks help guarantee that both images and labels match the model's expected input format. To deliberately cause overfitting, we restrict the training data to a very small subset of 500 samples. We form this reduced dataset by taking the first 500 images from the original training set along with their labels. Because the model now sees only this limited data, it is likely to memorize these examples too well. This setup is intentionally designed so the model overfits the training data. We set the validation set size to 2,000 images, so we have enough data to check how well the model performs. To build this set, we take a block of images from the training data that starts right after the small training subset and continues for the length of the validation size. This way, the validation images are different from those used for training, which helps us test how well the model generalizes to new data. We select the corresponding labels for these images so that each validation image has the correct label. We first convert the training data to a floating point format, then scale the pixel values by dividing by 255 so they fall between 0 and 1. This normalization helps the model train more effectively by keeping all input features on a similar scale. We apply the same normalization to the validation data, so it is processed consistently with the training data. Finally, we normalize the test data in the same way, ensuring that evaluation happens under the same conditions as training and validation. We define a function that builds a simple convolutional neural network for CFAR10 images using a sequential keras model. It starts with a two-dimensional convolutional layer with 16 filters and ReLU activation, taking 32 by 32 by 3 images as input, followed by a 2 by 2 max pooling layer. A second convolutional layer with 32 filters and ReLU activation is added, then another max pooling layer, and the result is flattened into a one-dimensional vector. This is passed to a dense layer with 64 units and ReLU activation, and finally to an output dense layer with 10 units and softmax activation to produce class probabilities. The model is compiled with the Atom optimizer, sparse categorical cross-entropy loss, and accuracy as the evaluation metric, and the function returns this compiled model ready for training. We begin by building two identical convolutional neural network models using the same model creation function, which sets up layers such as convolutional, pooling, and dense layers. One model, called the overfit model, is trained on a small dataset without any regularization, so we can observe overfitting. The other model, called the regularized model, starts with the same architecture, but later has regularization techniques added to reduce overfitting. By comparing these two models, we can see how regularization affects performance. We build a sequential convolutional neural network in keras for CFAR10 image classification. It starts with a two-dimensional convolutional layer using 16 filters with ReLU activation on 32 by 32 color images, followed by max pooling to reduce spatial size and a dropout layer that randomly drops a quarter of the activations to limit overfitting. A second convolutional layer with 32 filters and ReLU is added, again followed by max pooling. The result is flattened and passed to a dense layer with 64 units and ReLU activation, then another dropout layer that drops half of the activations. The final dense layer has 10 units with softmax activation to produce class probabilities for the 10 CFAR10 categories. We now compile the regularized model to prepare it for training. It uses the Atom optimizer, which is well suited for efficient learning, especially when gradients are sparse. The loss function is sparse categorical cross-entropy, which matches our multi-class classification problem with integer labels. We also track accuracy as a metric, so we can monitor how well the model performs during training. We train the overfitting model using the keras training function on a very small dataset and its labels. The model runs for 10 epochs, meaning it goes through the entire dataset 10 times and uses a batch size of 64, so it updates its weights after every 64 samples. We also provide separate validation data to check how well the model performs on data it does not directly train on. The training is run in silent mode without printing progress. This setup is intentionally chosen to demonstrate how a model can overfit when trained too much on too little data. We train the regularized model using a fit procedure that takes the small training dataset and its labels as input. The model is run for 10 epochs, meaning it passes through the entire training set 10 times. A batch size of 64 controls how many samples are used before updating the model's internal parameters. We also supply separate validation images and labels to track performance on unseen data during training. The training is run in silent mode, so no progress messages are printed. We examine the final training and validation metrics from the overfitting model to understand its performance. The last recorded training accuracy shows how well the model fits the training data, while the final validation accuracy reflects how it performs on unseen data. Similarly, the final training loss indicates how closely the model matches the training targets, and the final validation loss shows how well it generalizes. Comparing these training and validation values helps reveal whether the model is overfitting. We evaluate the regularized model by looking at 4 key metrics from its training history. The final training accuracy shows how well the model fits the training data, while the final validation accuracy shows how well it generalizes to new, unseen data. We also examine the final training loss to understand the remaining error on the training set, and the final validation loss to see the error on the validation set. Together, these metrics summarize the model's performance and help us detect signs of overfitting. We report the training accuracy of the overfitting model rounded to 3 decimal places, and then its validation accuracy, also rounded, to see how well it generalizes to new data. We also print the training loss, rounded in the same way, to show how closely the model fits the training set. Finally, we print the validation loss, again rounded to measure how far the model's predictions are from the true values on the validation set. Comparing these 4 numbers helps us detect overfitting by contrasting performance on training data with performance on validation data. We report the training and validation accuracy of the regularized model, rounded to 3 decimal places, to compare its performance with the overfitting model and see how well it generalizes to unseen data. We also report the training and validation loss, again, rounded to 3 decimal places, to measure how well the model fits the training set and how it performs on the validation set. Looking at these 4 values together lets us clearly contrast the regularized model with the overfitting model and highlight the impact of regularization on performance. We first evaluate the overfitting model on the test dataset to see how well a model trained on a small subset performs on new, unseen data, and we focus only on the test accuracy it returns. Then we evaluate the regularized model, which uses dropout layers to reduce overfitting, on the same test data, and again look only at its test accuracy. Comparing these 2 accuracies shows how much better the regularized model generalizes than the overfitting model. Both evaluations are run silently by turning off detailed output. We evaluate how well each model generalizes by printing its test accuracy. First, we report the test accuracy of the overfitting model, rounding it to 3 decimal places for clarity. Then we do the same for the regularized model. Comparing these rounded test accuracies shows the impact of regularization on the model's performance on new, unseen data. This script uses TensorFlow and a small subset of the CIFAR10 dataset to demonstrate overfitting in convolutional neural networks. It trains one basic convolutional model and another model that adds dropout layers for regularization. On the tiny training set, the unregularized model reaches very high training accuracy, but performs poorly on validation and test data, showing clear overfitting. In contrast, the model with dropout maintains more similar accuracy across training, validation, and test sets. This comparison illustrates how regularization techniques like dropout help prevent overfitting and improve a model's ability to generalize. In this lecture, you learn to construct a convolutional neural network using conv2D, pooling, and fully connected layers in PyTorch. Train the CNN on a small image dataset using the standard training loop and appropriate loss and metrics. And analyze model performance using accuracy, confusion matrices, and simple error inspection. In the next lecture, Lecture B, we will go over transfer learning. Thank you for your attention. See you all in the next lecture.